question and you have difficulty asking in English, you can ask me in Urdu. I can bear with that. But try to ask in English. Okay, so we are studying the minimum spanning tree problem, the MST problem, and the computation problem, as you might remember, is that given an undirected weighted graph, we need to find the spanning tree out of all possible spanning trees whose sum of weight is the minimum possible. So I hope that part is clear. We have a weighted graph. We want to remove some edges so that what we get is a graph, and the weight is the minimum possible weight out of all the spanning tree. A spanning tree is nothing more than a tree a graph that has a single path between any two vertices, and all vertices of the original graphs are included. So the original vertices are included, but some of the edges may be removed according to need. So we saw that a naive algorithm would be to find all possible subtree, select the one with the minimum weight, but that we had seen is almost an exponential algorithm. This is a brute force algorithm, and brute force automatically indicates that it is exponential in time. And then we look at this figure that show the basic intuition of how any algorithm, and I'm saying any algorithm that solves the minimum spanning tree problem would need to work on. So if we make two partitions, one partition is on the left side, the other partition is this one on the right side. So a few edges will be joining these two parts of the graph. So the edge that we will be selecting is the one with the minimum weight. Okay? That's the whole idea. So this is actually a theorem, and if you want to write it more formally, in the book, it's chapter number 23, by the way, I think, 22 or 23. So in the book, you'll see a theorem that is more written in a more complicated form. I have tried to write it in a simpler form. So a theorem is something that is a mathematical fact, and it is always true. So this is a theorem, a mathematical fact that is always true for the minimum spanning tree for a graph theory. So if we have a graph that is weighted undirected, and A are some of the edges in the MST. So what we are trying to say is that we are building it in three-dimensionally. So we are adding edges one by one. So it runs in a loop, and in each iteration it is adding a loop, and at some particular time A is the edges that we know are in some MST. Some MST meaning one of the possible MST. So for any partition, so So the partition can be any partition, but it has to follow one condition only. And the condition is that it respects the cut. We'll see what we mean by respects a cut. So it's a partition that respects the cut. The edge with the minimum weight is a safe edge. So lightest is the minimum weight edge. And we call it a safe edge because we mean to say that it's safe to be included in MST. So we can add this one more edge. So initially, the edges that we have chosen for the MST will be all empty. In the first iteration, we will include one edge. In the second iteration, we will include another edge. And in each iteration, we will be including one edge at a time. So, and it will form one of the possible, at the end what we'll get is one of the possible MST. So not a particular MST, but a MST, one of the many possible MST. Don't worry if it's a bit confusing, I'll try to explain it over here. So, the thick edges are in A. Okay? So, these edges are already included in the MST. Let's say this edge, this edge, this edge, this edge, this edge. The thick edges that are drawn a bit fat. And the thin edges are not in MST. So this is not in A, which means that not in MST. And these edges, I don't know, this one edges, and there can be a few over here, some other graphs over here. Okay? So now what we need to do is to find a partition. So we want to divide it, so we can partition it in this way. And we say that the cut respects A because the cut doesn't go through any of these thick edges. Cut doesn't go through an edge in A. I hope it's clear. So as you can see, if we had drawn a cut like this, for example, something like this would not be a cut that is respecting A because it's cutting the edges that we have already included in A. Okay. So, if E is the lightest edge, so this is the lightest edge, so we can include this in A, which is the MST essentially.
So what do you mean by the lightest?
The minimum weight.
Sir?
And why is
Why
sorry.
aren't the lighter ones in the upper cut included in the
No,
Yes,
we
sir.
are looking for an edge that goes through this cut.
so how do we choose the set weight?
how do we choose the set? Right now, we are not talking about how do we choose. We are saying that if we choose a partition like this, this is possible. Okay, how do we choose it? It will come a bit later on. Okay? So, the logic behind this is that these are two parts. The tree, a part of the tree is over here, a part of a tree is over here. They need to be connected somewhere. These two parts have to be connected by one edge and just one edge only. So these two edges, the edge that will connect these two different parts will be the one that is lightest. Because if we choose another edge, say E dash, this would either be heavier than, more weight than E, which will mean that it will not be an MST. If we don't include any of these, that will mean that these two parts are disconnected. That will disobey the condition of a spanning tree. And if E dash and E has the same weight, that will mean they correspond to two different MSTs. I hope you understand. So if this has age H2 and this also has a weight of 2, so we can choose any of those. So essentially the MST that we'll get will have the same weight. Why can't we have two edges? Because that way it will form a cycle. Okay? So we can only have a single edge connecting any two parts, and that edge has to be the lightest possible edge that is connecting the two parts of the graph. Any question? So we had seen this graph that, so now we are kind of going to a bit of detail into whatever we have studied. So we'll look into more detail, look at some figures, what we mean by that. So this is a graph. We have not included any weights. We partitioned the graph. It has a black partition, a black set, and a gray set, and any these are two sets. So this forms a cut. There is a boundary between the two edges. This boundary goes through the edges that are connecting a black edge, black vertex with a white vertex, gray vertex. Okay? A black, so different colors are connecting to each other. Okay? So this is a partition. Now let's suppose that we are building the minimum spanning tree one by one. So now we have the blue edges are the edges in A, as you can see over here. So these are these edges. The blue edges, they are in A. Now we need to choose a partition so that it respects it. So can we say, for example, do a partition like this? Like this is one. No, because it is not respecting A. So there are many possibilities, but one possibility is that we do the cut like this. So this part becomes one color and this other becomes another color. So this one respects A. So this is a partition. So in the slide, this part, so there are many possible partitions that respects A. in the beginning there will be a lot of possibilities. Gradually, as we increase the number of edges in A, the possibilities of choosing between different partitions that respect A become smaller and smaller. I think this makes sense, right? So this is a partition that respects A. So which edge can we now include in A, in this set A?
F and B.
Sorry.
The one between F and B.
Yes. Yeah, we can include F and B. We can also, no, I think we can only include F and
So we can include G and D.
G and
D.
G and D. Let me see where D is.
Because
No, these are both in the same partition. So, okay, let me just try to explain. So one set is this one. This is one set. We have included, and the other set is this white one. So why cannot we include this one? Because they are both red color. They are both in the same set. So this cannot be included, but this can be included. G and H, that's correct. So that's another way that's light and crossing the partition. So there are two possibilities. So we'll just pick one of them. It can be any one of them or whatever the computer or your program finds first, that is the correct one. So it doesn't matter which one you choose as far as the algorithm is concerned. So this one is chosen. So this now becomes part of the MST that we are slowly building up. So we are building a minimum spanning tree, one edge at a time. So now the situation is this. So we need to choose another partition because the other partition is no longer respecting A, because that is included, that becomes a blue edge. So we now have to look for another partition, and what we choose is this. So it doesn't have to be 4, 5, 6 edges, vertices in one group and a few in the other. It can be just one vertex in one and all the rest in the other as well.
So इसमें J G हो जाएगा.
J and G हो जाएगा, ठीक है? So J and G would be the only correct option because it's 3 and 2, and the minimum weight one is
2.
2. So that one is chosen. Correct. So I think so what the theorem is claiming is that this way we can slowly build a correct minimum spanning tree. A minimum spanning tree that is actually the minimum. And I had shown you the reason. I didn't go into too much detail about that otherwise the two parts are disconnected, so there is reasoning behind it. It's not like it's something magically somebody thought of something magically. It has logic behind it. It has deep thinking behind it.
So
Okay. Right now we are not doing it randomly. We are doing it just to show it. Okay? The number of possible partitions is exponential, and so if we are trying to do it in a non-clever way, we'll look for a partition, check if it respects A or not. If it doesn't respects A, we'll look for another partition, until we find a partition that respects A, and then can take a lot of time. So this is just a basis of how any concrete algorithm will be working. ठीक है? The concrete algorithm are Kruskal and Prim's, and that we'll study later on. That essentially gives us a clever way of always finding the correct partition this way. So, just as I said, so here is the generic MST. Why did I write generic MST over here? Because it's not a concrete algorithm. Which essentially means not possible. So it's just a broad idea. So the generic algorithm is working something like this, that initially the set A is, so A is usually used for answer or algorithm, whatever the algorithm is calculating. So usually algorithm people use an A. So the answer that the algorithm calculates is given an A. It can mean an answer or it mean the algorithm. So it's empty. Then we have a loop, which checks that until A is not a spanning tree, we find a partition, then find a safe edge. So finding a safe edge means first finding a partition, checking that it respects A, then finding the minimum weight edge, and that is the safe edge, and we call it E, I think, and then we include it in A. So in each iteration, one edge is included in the minimum spanning tree that we are constructing one by one. So the invariant is that what is this loop trying to do? This loop is trying to do is that in every iteration of the loop, the A that is calculated is always a subset of edges in MST. Yeah, that's right. So it's always a subset of the minimum spanning tree. So in more detail, you can read it that initially A is a subset of the minimum spanning tree, and after finding the safe edge and included in there, what we get is also a minimum part of the minimum spanning tree. So your question was, Muzammil, how do we find a safe edge? How do we find a partition? And that's why it's highlighted that this generic algorithm doesn't give us a quick and easy way of how to do it. And that's the tricky part. So some other people have developed algorithm that cleverly computes partition. It doesn't say it computes a partition, but we'll look at it and we will always see two partitions in it that respects A. So the algorithm essentially follows the theorem that we saw a few slides before, that whenever we find a partition that respects A and we include the minimum weight edge, the edges that we'll get will be a subset of the ultimate minimum spanning tree, and it will be the correct answer, minimum spanning tree will be calculated. So there are two concrete algorithms, and many of you would have studied it or seen it before also. So one is called a Kruskal's algorithm. Who have studied it? So it's a pretty old algorithm. The other was by a person called Bridge, and he developed an algorithm in 1957. So it's like long time ago. And now we look at these two algorithms, how these two algorithms work. आ जाए यार आप जरा आगे बढ़ जाए, आप दरम्यान में से उधर सामने आ जाए. So this is the Kruskal's algorithm. So Kruskal algorithm essentially builds a forest of trees. It uses the disjoint set data structure. So it has sets that are just disjoint. So what is a disjoint set? That if there are multiple sets, this set has A, B, then this set has Z, X, Y, something else has D, E, and they are different. If the same character, the same element is over here, it will not be a disjoint set because they are, so this will not be a disjoint set, so this cannot be a disjoint set. So in order to maintain disjoint set, many data structures are available that maintains disjoint set, and there are different types of implementation. We will not go into detail of how those are implemented and what their time complexity is, but they have these functions. One is called a make set, so it creates a new set and starts it with a single element called X. The other function that it has is called a find set. So find set, you give it a element of a set and it returns some ID, which can be a number, say 23, 54, 1, whatever. So it's an identifier of which set this element belongs to. Remember that example? So if I give, this is set 1, this is set 2, this is set 3. If I say find set Y, it will return me 2. So it will give me an identifier. So this will be helpful for checking if two elements are in the same set or not. Okay? If the ID matches, so they belong to the same set. So A and B have the same set and their ID will also be the same. So this equality will be true. And if they are not in the same set, so we'll get a false. In this case. And union is that joins the set containing the element X and Y. So if I say union, now I'm talking about this example, say B and B. So what it will do is that it will make these two elements into a single set. Hopefully these basic things are, so it's pretty simple. Make set, it creates a set. Find set, it gives you an ID of the set. You give it an element, it gives you an ID. And with this you can see if two elements belong to the same set or they belong to a different set. And you can merge two sets just by giving a union function. So you give it an element and it will kind of union merge them together. So this is the algorithm. So now this is a concrete algorithm. Okay? So what it does is that it first, this is like the same as in the generic algorithm. Okay? So we start with an empty set of edges, then we create a set for each vertex. Okay. So we create a separate set for each vertex. We sort the edges. So we sort the edges from the smallest to the largest. Okay. And for each edge, we one by one select the edge, and now we are selecting it from the sorted array of edges, starting from the lowest and going one gradually to the highest. So one by one we select an edge UV. So the two endpoints are U and V, and we check if the two U and V belong to separate sets or the same set. If they belong to the different set, we include it in A. This edge is included, so this is the set E, and we merge the two sets together. So I'd like you to go through this algorithm of it.
So for each edge U and V, so E is the total number of edges.
E is the total number of edges. So basically, we are picking one edge at a time.
Yes.
Okay? Looking at this two endpoint, and we are calling one endpoint as U and the other endpoint as V. So in each iteration, the U and V will change. These are variables essentially. U and V are variables. So in one iteration, U can be vertex number 10, V can be vertex number 50, and in the next iteration, U can be vertex number 5, and V will be vertex number 15.
As it goes through entire graph.
It goes through the every edge one by one,
Yes.
and see if the two endpoints are in different sets or in the same set. If it's in different set, it will merge them together, include that edge in A. And what is it?
So it's a union of both edges.
A. What is A? What is A?
So ये हमें मिनिमम वाला देगा, मिनिमम स्पैनिंग वाला.
Yeah, this is the answer. The building. Incrementally one by one. Any other question?
Sir, did you explain the function make for
So make set is saying that we build a set for each. I will explain it to you in the next slide. It creates a separate set for each vertices. So the graph that I drew had 4 vertices, so it will create a set 1 containing just the vertex A. It will create a set number 2, will just contain B, and so on. So this is our input graph. So first of all, we create a set for each vertex. So imagine that every vertex is in a different set. Okay, Fazan? Okay? Every vertex is a different set. And then we sort these edges in non-decreasing order, sorted in the normal way. Okay? From smallest to largest. So imagine all these edges sorted. So in the beginning there will be the edges of weight 1, 1, 1, 1. Then there will be the edges of weight 2, 2, and so on. It will go to 3, and I don't think there is any edge that is larger than 3. Okay? So there will be repetition in the sorted. So we'll pick the edge, the first edge. So now this line comes. So it will pick the edge from the sorted array of edges, and it will be one of the lowest one. So let's imagine that it picks this one. I hope you can see it, the gray one. Okay? So right now, I and F are in two different sets. Remember, no
Yes.
union has been performed yet. So since they are in two different sets, these sets will be merged together, and this edge will be included in A. And this we will represent by this blue line as before. So the gray edge means that we are checking if it's in the same set or not. When I make it blue, that means that I have executed these two lines. So they were actually in two different sets and they were merged together. So now they are now
In same
the
set.
same set. Yeah, so this becomes one set. Similarly, the next edge that it will pick is this one. I hope you can see it. Okay? It will check if it's in the same set or not. They are also not in the same set, and it will be included. Okay? And so on. It will check this one. So now, what do we have? So we have one set is this one, and one set is this one, and all these are
Independent.
individual sets.
Individual sets.
These are individual sets, and so on. So the edge that is joining F and B are in two different sets, so it will be included in A.
So by the end of this loop, entire graph will be included in one set.
Minimum
Let me ask
spanning.
you a question. How is it following the minimum, the theorem that we studied about partition and respecting?
So, because we are considering the minimum edge connecting the both vertices. One.
So, okay, we are considering this one, okay? So I can say that this is one part, this is one set, and the whole other graph is in the other set. If we look at it in that way, so it's not like two different sets, and it gives us a partition that is respecting A. So it's important to understand that not just the working of Kruskal algorithm, but also how it corresponds to the theorem. So it's actually an algorithm that's following the theorem. So we'll go through it a bit quickly here. So this is included, No, but okay, so this is also included. This is also included. This is also included. This is also included. Will this be included or not?
No.
It will create
No,
a cycle.
because it is connecting. So all these are in like it is forming one set. Okay? So it's forming this set. Yeah. So it's within the same set. I hope I can make it. So since it's in the same set, so we will not include it and we will skip through it because this the if condition is false, so it will skip it. So it will check, but then it will not include it. And then we go to the next one. So it comes to this one. So this will also be not included because it's connecting two edges that are in the same, yeah, they are kind of connected with each other already through the blue lines. Okay? And similarly, will this be included? Yes. Yes, this will be included. Yes, this will be included. Will this be included?
No.
No, this will not be included.
No.
No.
Yes.
No.
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 No. No.
And with that, I think the algorithm ends because it starts from the edges of weight 1 and gradually increases the weights and checks it. So the objective of sorting is to first include the edges with the minimum weight,
Safe edges.
and the safe edges, the lightest edges first, and gradually go towards the heavier edges. And how does it follow the whole thing that we were talking about having two partitions? Because we can consider whatever U is to be in one set and all the remaining in the other set, and then this thing is checking if it's respecting or not. ठीक हो गया?
Sir, as you said that we first include the edges with the light weight. So where the algorithm is checking the edges with the light weight.
We have sorted it.
Okay.
We have an array. So we first have edges with one, then we get edges with two, and so on. In the end, we get edges with two. So we start with from here. So we first check this one. So we are first giving the light edges a chance. Priority. Because we want a minimum spanning tree, the edge with the tree with the minimum possible total weight. Okay. So we won't go into too much exact detail, but we need to make set calls.
Yes, sir.
The exact complexity will depend on how the data structures is implemented, and this is covered because we are running the loop for every vertex, and for every vertex we are making a set, so this will take some time in making the set. It will probably be a very small time. And then we need E log E time to sort. We are using something like quick sort or merge sort to get efficiency. And then for each edge, we are running this loop. This loop is being run for each edge. And then for each edge, we do this thing, 2 find set, so that's why it's written 2e times find set operations. Or in any tree, we will have v minus e edges. At most, we will be doing union e times. So every edge will be union. So that's like the worst case time complexity. So I think we will end this part over here.